All right, scholars. Now we're going to use an example that actually can be adjusted real quickly to real-world problems. We're going to use length to find geometric probability. We're going to ask to find a point chosen randomly on segment PS. So somewhere on here, I'm going to find a point. I want the probability of where it's going to land. So the first one is I want the probability that it's going to land on segment RS. Well, what's your total sample space? Well, it's the whole thing, right? So that's really the length of segment PS. Well, that would be 25 because 7 plus 13 plus 5 is 25. Then we have the length of our segment RS. Well, that would be 5. Well, I get 5 over 25, but probability we know is going to be at 1/5. Oh, and one thing I want to emphasize with you, probability can be done in decimals, fractions, or percentages, but they all have to be under 1. To have the probability of 1, that means without a doubt something will happen. And the only thing I know for sure that works for number 1 is the probability that we all have physical death, that we'll all die someday. That's the only thing I can for certain say about any human being here on the earth. Now, those of you who just brought up the exceptions in the Bible, I know what you mean, okay? But for the most of us normal human creatures, okay, we have the probability of 1. So you always want to look for something that's under 1. If it's over 1, you did something wrong, okay? So that's the probability of 1/5, 5 out of 25. It's about 20%, or 0.2, right? So the next one is, what's the point? I want the probability of the point that is on segment PQ or segment QR. Now, if it's either or, is that smaller or less than? Yeah, it's both of them. All right, smaller or less than, excuse me, smaller or greater. It's a greater chance of something landing on there. So I want to add those two together. So really, I need to have their two lengths. 7 plus 13, that's 20. But however, my sample set is still segment PS, so that's still 25. That's 4/5, about 80%. If I was going to pick a point on that line, 80% chance I'd pick it on there, on segment PQ or QR. But now, here's another one. I really like this, is what is the probability that a point is not on segment QR? Now, there are two ways to calculate this. A lot of you went like this, probably not on segment QR. So you literally go, all right, the probability of, the sample space is 25, but if it's not on QR, I pick 7 and 5, I know that's 12. That's 12 25ths. Great. But another way of calculating probability is, if I want to figure out what's not on segment QR, I just go 1 minus the probability of QR actually happening. So I go 1 minus, what's the probability of QR? Well, that's 13 over 25. Well, do I still get 12 25ths? Yeah. Does it really matter which one of those ways did I get this? No. Adding them together or subtraction? It doesn't really matter. Now, here's one of those cool examples of kind of a real-world thing. I lived in Houston, Texas for a while, and one of the biggest complaints about Houston, Texas was the downtown traffic. Now, understand it's nothing like downtown traffic in Chicago. I will never, ever compare it in that sense. But it was really hard for people to get to work on time or to leave work. And one thing that a new mayor, Mayor White, decided was he was going to study the cycles of the light signals. And he actually used probability in studying the cycles, kind of in this very simplified version of it, and he reset the light signals in downtown Houston. Guess what? Traffic went better. So he used geometric probability and the study of the light cycles to change and improve the traffic pattern in downtown Houston. So that's kind of one of those cool, kind of neat things that you can do with math. So here, we're talking about just a simple walk and don't walk symbol, okay? Now, when we're doing this, it says we have a pedestrian signal at a crosswalk that has the following cycle: walk for 45 seconds and don't walk for 70 seconds. What is the probability the signal will walk when you arrive? Hint, use a line segment to represent one complete cycle. So I'm going to do a line segment. Here's my one complete cycle. But it should be divided into two cycles: walk and don't walk, right? So walk cycle is for 45 seconds. The don't walk is for 70. So with this, so the probability, I want to know what's the probability of walk. You have to use the length of the line segment. What would be the length of this whole line segment? That's right, 115. 45 plus 70 is 115. But then I want to use walk, the probability of walk. So that'd be 45 over 115. Now, I still should be able to reduce this, but that's my probability so far. 45 over 115, what does that reduce down to? 9/23. So you have a 9 out of 23 chance, basically, that you are going to hit the walk cycle when you go in there. So think about it like this way. 23 times, if you walk up to this light randomly, there's 9 chances you'll walk up there on walk. And you could keep going. The rest of those chances, the other 14 chances, means you're stuck there at the don't walk sign. So hopefully that kind of gives you an idea. So that's using length and cycle to work with it. The next one is the spinner. And this is using angles to do probability, or you can say even arc length. We've all played with spinners. Pardon me. It's late in the evening while I'm doing this, so apologies. With spinners, hello, how many of you ever do chutes and ladders? I tried to cheat and I still couldn't win in this game. And it's divided in colors, and so I'm going to help you with the colors because it's very hard to see. The top one is a 140-degree angle, or 140-degree sector right there, is supposed to be the yellow one. This is supposed to be green. This one over here is blue. And this section on the spinner is red. Casinos use these the best. The chance to hit one little number on a big roulette wheel and all that type of stuff, all using probability to their advantage. And so here, let's practice finding this. Now, if I know in angles, I want you to remember, what do all 4 of those angles have to add up to? 360. So it's always going to be over 360 degrees because we're working in a circle here. So the probability that I would land on yellow, well, I know 360 degrees is my choice, but yellow is 140. Now I'll just reduce your fraction. Take 10 out of both. I know 2 can come out of both of those. The probability would be 7/18. Then we have the probability of the pointer landing on blue or red. So we go probability of blue or red, which means I want to count both of those because blue or red is smaller individually, but together they're a bigger value. So it's still over 360, but when I have blue or red, I just take 60 plus 108, and that's 168 over 360. And when I reduce this one down to, I can take out with this one, and I can get 7/15. Now, for those of you who want to know, like, how in the world do I get 15? Well, remember, 30 goes in there 20 times, so that means 60, right? So, pretty easy. I mean, 40 can go into both of those, so it works out pretty easy. All right. 40 cannot go in there. I cannot talk today. Just trust me, it's 7/15. I can't do my math all of a sudden. Bad day. All right, we're going to use the same spinner, so you're going to see me actually stop this video once we're done using the spinner, and then we'll do the last one together. But the first one is, what's the probability of not landing on green? So probability of not green. I think the easiest way of doing this is actually to count the other ones up. So the probability of not on green is you have 140 plus 60, which is 200, plus 108, which is 308. So the probability of not in green is 308 over 360. What do we get when we simplify that? That's going to be 77 over 90. Now, 4 can come out of both of those is what I took out. So that's the probability there, 77 over 90. Now, we're going to say above, all right, or other page. Use the spinner above or other page to find the probability of the pointer landing on red or yellow. So doing the same thing here, I get red or yellow. It's still going to be over what value? That's right, 360. So the probability of red or yellow, so 60 plus 140, that's 200. And the cool thing is that reduces down to 5 ninths. 5 ninths. All right, we're going to take a quick pause here, and then we'll finish up the last problem together.